Okay, once we establish the correspondence between the electromagnetic case and mechanical case, we can easily write the equations of solutions we already know for the mechanical case, and then we can translate it to the case of electromagnetic oscillation. We're going to do that in just a minute. Okay, but before we do that, let's take a closer look at how K and M translate to the electromagnetic case. We know X becomes Q and V becomes I, right? That all makes sense. What about K? What about M? First of all, take a look at K. K is the spring constant, right? A large K means the spring is very strong, which means you give it a little bit of stretch, it gives a lot of force. Okay? It gives a lot of force. That's what a strong spring means, large K. Okay, now, turns out K corresponds to 1 over C, not C itself. Okay? Not C itself. Does that make sense? This seems to say that a strong spring in a mechanical case is analogous to a very small capacitor. A very small capacitor. Okay, what does a capacitor do when you give it some charge? Remember, charge corresponds to X, right? So when you pull the mass, when you pull the block by a certain distance, it is analogous to charging the capacitor with a certain amount of charge Q. Okay, what does a large spring constant mean? It means you give it a little bit of displacement, it gives you a lot of force. Okay, and then if you translate that to the case of a capacitor, if you have a very large capacitance, then you can put a lot of charge on it, and very little happens, right? It doesn't respond with a lot of EMF. Okay, actually, with a lot of potential difference, right? This means that a large capacitor behaves just like a soft spring, not a strong spring. Okay, a soft spring, because a soft spring means you pull it with a great deal of displacement. It doesn't really respond with a lot of force. It doesn't really care. Okay, so you see, it is not only mathematically required to replace K with 1 over C, not C itself, but 1 over C. It also makes sense physically. Okay, a very strong spring corresponds to a small capacitance, and a weak spring corresponds to a large capacitance. As a matter of fact, if the capacitance is really small, what does that mean? You give it a little bit of charge, it's going to give you a whole lot of voltage drop. Just like a strong spring, you give a little bit of displacement, you end up with very large force. Okay, so you see K corresponds to 1 over C. And what about M versus L? What's M? M is the mass, right? It is the ability of a system to resist what? To resist acceleration, to resist dV dt, that is. What about L? Well, L is the ability of a system to resist any change in what? Current, okay? Because, in order to drive a variable current through an inductor, you have to overcome its induced EMF, which is proportional to L, right? So, a large M means it is difficult to cause an acceleration, or dV dt. A large L means it is difficult to change the current, in other words, to cause di over dt. That is why M and L correspond to each other. Okay? And we can call L some sort of electromagnetic inertia, just like M is the measurement of inertia. So this correspondence makes a lot of sense. We're going to continue with this table later when we have, of course, here you also have what? You also have a resistor, which we didn't put in the system yet. We will. Okay, and we'll see what happens to the mechanical system. What kind of correspondence would you have for the mechanical system? We're going to do that later. But now that we have the analogy, we are now ready to solve the electromagnetic oscillation, or LC circuit. In the LC circuit, what kind of solution do we have? How is Q going to depend on time? Well, mechanical system, we have X equals A cosine omega t plus phi naught. Remember that? Okay. Translating that to the electromagnetic case, what do we have? We're not going to start over again. We're just going to use the correspondence. X becomes what? Q, right? So Q as a function of time is now what? Instead of A, which is the maximum value of X, I have Q maximum, right? Q max. And then what? Cosine. Also omega t plus phi naught. Phi naught is just initial phase, depending on when you start your timer. omega, in a mechanical case, omega was equal to the square root of what? K over m. Right? K over m. In the electromagnetic case, therefore, what do you think omega should be equal to? Equal to what? Square root of, now what is replacing K now? 1 over C. Okay, what is replacing M now? It's L. Okay, so it's 1 over C and divided by L, it is 1 over LC. This is the frequency, is the angular frequency of an LC circuit. It will oscillate with this much angular frequency, just like a spring mass system will oscillate with this much angular frequency. Okay, so you see, you find the solution right away without starting from scratch, because we already have these solutions, so we can just follow the results and get the result right here. Okay, now it is clear that the total energy in electromagnetic form should be conserved in an LC circuit, because we showed that Kirchhoff's rule is totally in agreement with the conservation of energy, and this, of course, this is solved from the Kirchhoff's rule equation. But I want to show that explicitly, just to drive the point home. That is, you have conservation of energy. Okay, in other words, electrical energy plus magnetic energy equals a constant. I want to find the total energy of the system given Q. Okay, actually, given Q, you know what I is, right? The current I is dq dt. We all know what that is. Okay, you do that, you find it is equal to what? Negative omega Q max, and then what? Instead of cosine, you have sine. Right? Sine omega t plus phi naught. Right? Okay. Given Q and I, can I find the electrical energy and the magnetic energy of the system? Of course I can. Okay. So you have UE, the electrical energy, equals what? Q squared over 2c. Right? Q squared over 2c. And that equals to Q max squared over 2c cosine squared omega t plus phi naught. Okay, omega t plus phi naught. And what about UV, the magnetic energy stored on the inductor? That's 1/2 L I squared. Okay, I know what I is. So it's 1/2 L times what? I squared, and then we have omega squared, Q maximum squared, and then sine squared. Right? Now, let me add them together. Okay, so total energy is UE plus UB. We expect it to be a constant. Do we get a constant? Okay, there is a sine squared function, there's a cosine squared function. Both of these change over time. And the only possibility for them to add up to a constant is if this prefactor equals that prefactor. That way, I can take them out, and what's left is sine squared plus cosine squared, which you know, of course, equals 1, a constant. Okay, so conservation of energy would be true if these two prefactors are equal to each other. Well, are they equal to each other? Well, we know what omega is. Omega equals 1 over square root of LC, and therefore, omega squared is just 1 over LC. So, I can rewrite this expression. What is that? It's 1/2 L omega squared. So it basically is L times 1 over LC. Right? L times 1 over LC, because omega squared is replaced by 1 over LC. So it's just 1 over 2c. And then Q maximum squared. You see, they're the same. This equals that. So therefore, I can take either this one, that one out. They're equal to each other anyways. And what I have here is Q maximum squared over 2c. And then you have cosine squared, blah, 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 plus sine squared. Same argument, omega t plus phi naught. And indeed, this equals a constant. Okay? This equals a constant, which I can write as Q maximum squared over 2c. I can also write it as 1/2 L I maximum. Same thing. You see, what's Q maximum? Q maximum is the maximum value of the charge on the two plates. And when that Q reaches a maximum value, all the energy is in electrical form stored only on the capacitor. What is the current at that moment? 0. Okay, so at that moment, the energy on the capacitor is Q maximum squared over 2C. It is also equal to the total energy because at that moment the magnetic energy on the inductor is 0 since the current is 0. But we can also add it's 1/2 Li maximum squared because a quarter of a period later the charges will disappear from the capacitor, and at the same moment the current going through the inductor will be a maximum. The energy of the system is entirely magnetic. It's 100% carried by the inductor. So therefore, you have 1/2 Li maximum squared. That is not only the energy stored on the inductor at that moment, it is also the total energy of the entire system. Okay, so these two should be equal. They're both equal to the total energy of the system. And in fact, we can show that this is indeed true because after all, you look at the expression for the current. This is I maximum, right? I maximum because I equals I maximum times sine function, which never goes beyond 1. So I maximum is Q maximum times omega. So with that you can show these two are equal to each other because I maximum squared, in fact, I maximum squared is omega squared Q maximum, and omega squared Q maximum, if you square it times L, don't you get that, right? Isn't that equal to 1/2 Q maximum squared over C? All you have to do is to make sure that you use omega equals 1 over square root of LC, so you can easily go between this and that. Okay, it makes total sense because it basically is saying that the maximum energy carried by the capacitor equals to the maximum energy carried by the inductor, and they're both equal to the total energy of the system. Okay, so that is how we study the energy conservation of an LC oscillation.